Okay, so what are we going to talk about today? We're going to talk about here, A is matrix, and X is vector. So you have a matrix and a vector is another vector. Now I'm going to write down what's in the beginning of your book, the interpretation of this, and then I'm going to do something that's not in your not in this section, but I think it's best that we tackle it early on. I'm going to show you how to multiply matrices. Okay, so let's set the symbols here. Let me interpret this for you. A is matrix. So what this notation means, A is the matrix. This lives in, and this notation means M rows by N columns, and all the entries are real numbers. So it's an N by N matrix, and let's say that, well, we call them vectors. A1, A2, N. So A has N columns, so there better be N column vectors. And let's say that X is X1, X2, Xn. So it itself is a column vector with N entries in it. Then AX, so when I write this, so this is kind of the theme of our section. What does it mean for me to take this matrix A times this column vector X? This is the same thing as, say, X1 times the first column plus X2 times the second column, all the way up to Xn times the nth column. So let me give you an example. For this example, I'm going to let A equal the matrix 3, 0, 2, 1 minus 1. So this matrix is 2 rows by 3 columns. This is a 2 by 3 matrix here. And suppose that I multiply it by the column vector. So according to this definition here, this is, let's see, X1 times the first column plus X2 times the second column plus X3 times the third. Everybody okay? And actually, if you wanted to sort of consolidate, you could write this as a single vector. Because this one is 3x1, x1. 0 times x2 is 0. And 2x3, 4x. So you actually could write this. This one as, for some reason, zero blank here, sorry about that. So you actually could write this as the single vector. 3x1 plus 2x3. And then my second entry would be x1 minus x2. So notice what I got was a 2 by 3 matrix multiplied by a 3 by 1 column vector gives me a 2 by 1 vector. Now, I don't like the fact that your book doesn't do this yet, so I'm going to do this yet. I'm going to show you how to multiply matrices in general, because really that's what we've done here, right? We just multiply matrices because if you look at this big picture, what is A? A is a 2 by 3 matrix. And what is X? I mean, I call that a vector, but that's really a special case of the matrix, right? X I've got there is a 3 row by 1 column matrix. Okay? So, and this will help. How do you multiply 2 matrices? Well, the first thing to know is you can't just willy-nilly multiply any 2 matrices that you encounter on the street. They have to have certain matching. So, if A is anyway, and B is N by K matrix. If you look at the matrix AB, you can actually multiply this. You get a new matrix M. So now, this one was N by N rows and N columns, right? And this one was N by K. Any guesses as to what the size of the resulting matrix? Yes. What's that?
Okay.
Very good. So this is sloppy, right? And so if you tell me where I told you this, I'll lie and say it didn't because it is kind of sloppy. But you sort of think it's in out, you get it in by K. And that's actually what you need to be able to multiply the matrices. The number of columns here must equal the number of rows here. You have to have that match. Notice that we can multiply A and B because I have a matching right here, right? It's not necessarily true that you can multiply them the other way. Yes.
Is that rule always true, or can you do it through transpose? Like if you transpose matrix?
Yeah, but then you're not multiplying the same matrix because the transpose is like solve, right? We'll get a transpose later. Okay, let me show you how it's done. Right. So let's I'm going to kind of do this via example. Let's put something formal at this point. So let's look at our matrix that we had before. 3, 0, 2 times 1 minus 1. Something different here. This, by the way, is a 2 by 3 matrix. To be able to multiply it by something, what do I know about the next matrix? It must have 3 rows, right? It has to have 3 rows, or I'm totally hoax, right? So I'm going to make something with 3 rows here. Let's go 1, 2, 3, 4, 5, 6. Now, whenever I multiply matrices like this, I think to myself, what do I expect to get, right? What size do I expect to get? Yeah, I expect to get a 2 by 2. And actually, I'm going to make it bigger. 2 by 2. It's a little bigger here. Now, a 2 by 2 should have 4 entries, right? What entry do I get for the first row in the first column? Well, it's first row times first column. Notice there's a match. You can sort of set this up. This times this, this times this, this times this. So what do I get here? 3 plus 0 times 3 plus 1 times 5. And that little zipper makes the first row first column. What if I want the first row second column? Then multiply the first row by the second column. And now you see why you've got to have everything match up, because otherwise it doesn't make any sense. What happens here? 3 times 2, 0 times 4, 1 times 6. Okay, so 2 more to go. We now need a second row first column. So multiply your second row times your first column. And that's going to be 1 minus 3 plus 10. And finally, second row, second column, 2 minus 4 plus 12. And so the resulting matrix is 8, 12, 8, and let's see how to do it. Let's do one more. Actually, for this particular example, you can do it in the other order, can't you? Right? Because you can multiply 3 by 2. So let's do that. Let's do it in the order. 1, 2, 3, 4, 5, 6. This is a 3-row by 2-column matrix times the matrix 301. 1 times 1, 2. And this should result in a 3 by 3 matrix. Everybody okay? All right, let's zip it up. Let's see how it works. Let's start with the first row and first column. This row times this column. So it's 3 and 2 is 5. Everybody okay with that? I want now the first row and the second column. So that's 1 times 0, 2 times -1, minus 2. Now I want the first row and third column. So that's 1 times 1, which is 1, 2 times 2, which is 4, so that gives me 5. Okay, so okay, now I need the second row first column. 3 times 3 is 9, and 4 is 13. Second row, second column, 3 times 0 is 0, -4. And finally, the last second row, last column, third column is 3 and 8 is 11. Finally, to finish this off, we just now need to get the entries in the third row. So third row, first column, that's 15 and 6 is 21. Here we get 0, -6. And finally, we get 5, 12, 7. Notice you can actually multiply this in both directions here because we kind of got lucky on the sides. But notice that you get 2 very different things. Multiplying A times B gives you this 2 by 2 matrix, and multiplying it in the other direction gives you this 3 by 3 matrix. Any questions on it? All right. Okay, so let me kind of tie in here. So in your book, one of the things that I kind of quoted with a little bit about is that first theorem that I gave you about, okay, AX plus B just means this. It's X1 times the first column, X2 times the second column. really what they're doing is disguised. It's exactly this matrix multiplication. Right, because suppose that A is, let me do this here. So suppose that you have this matrix here, so I'm writing it all in letters so I can get a nice formula. So notice what your book called, this is what your book called A1 hat. This is A2 hat, A3 hat. Finally, AN hat. These are just the column vectors in the matrix. Right? And if we have X is X1, X2, Xn. Then if you use this matrix multiplication rule that we have, so I'm deconstructing your book's definition. Yes.
So it actually does bother me. How can you just switch the order of operations, like multiply 3 by 2 by 2 by 3 and get something completely different?
Well, I mean, it's not even the same size, right? I mean, because orders of operations, even if they're the same size, if you multiply matrices in two different orders, it does not have to be the same thing. And there's an important reason for this. Let me ask you this. Y'all remember doing function composition in calculus? Right? Remember all that? There's no reason for that. Really what you're doing when you're multiplying matrices, we're going to see this later, is you're composing functions, right? And there's no reason why composing functions in two different directions is the same thing. For example, if you have, so let me just take a little segue here. Suppose you have these two functions, right? If you do f of g of x, this is sine of x squared. Everybody agree with that? If you do it the other way, this is sine x and then square the thing. These are not the same thing. Because in particular, this one can never be negative. But this one surely, right? Just let x be square root 3 pi over 2 and you get negative 1 this. Right? So composing functions in different directions does not give you the same thing. And it's the same principle here, right?
But with the matrix, can't you transpose it to get that order?
But when you transpose it, it's a different matrix. We can talk about that further, like we get a little more in detail. But so if I take A, which is an n by n matrix, and I take X, which is a vector, it's a column vector. This is a n by 1 matrix. What do you expect this to go to barf out? It should be an n by 1 matrix, right? In other words, it's a column vector. And let's see what the entries are. Well, let's see. It's this row times this column, right? So what do we do? Let's like first row, first column. There's only one column here. So this is A11X1 plus A12X2 plus A1N. And there's my entry up there. What's the next entry in my M/1 matrix? It should be the second row times the only column I've got. So it's A21 plus A22 plus A2N, like that. And I keep going. And in fact, what's the last entry? It's the last row times this column. So this is AM1 X1 plus AM2 X2 AMN X. Everybody comfy with that so far? And this is the way your book goes. Your book kind of picked it apart this way. What your book did is it broke this out of separate columns. Notice there's a common factor of X in this first column. So this is actually X1 times the column vector A11, A12, A1N. I'm sorry. And this is turned around 1. And this is X2 times A12, A22, M2, Xn times A1N, A2N, A. So basically, it's exactly what your book said. It's X1, A1, it's X2, A2. Where the A's with the hats on them just represent these column vectors from the matrix. Yes.
You're doing like that A1 to A2. I thought it was the other one, A2 to A2.
No, I'm reading off the columns here, right? So it's X1 times the first column there, and X2 times the second column. Everybody, okay with that? Other questions? Okay. Let me give you a theorem. Now that we've kind of multiplied these matrices and sort of deconstructed what these column vectors mean. Here is very useful. Theorem. Remember this notation. Now, what is scary just means A is an M by N matrix with real integers. Suppose we have this matrix. The columns, I'll call it A1, A2, AN. Those are the column vectors. And B is in R. And of course, that last bit just means B is a column vector of size n, right? So it's a column that's n tall. AX equals B has the same solution set as X1, A1, and really all this is just me writing down what this means, right? Because we already said that AX is equal to this thing on the left side of this equation. Let me add a little more, which is the solution set corresponding to the augmented matrix. A1, A2, AN. Okay. So in other words, if I want to solve this linear equation, so to speak, really what I'm doing is I'm solving a system of linear equations, which is the same as solving this whole augmented matrix. So in particular, let me make the following observations. So so the equation, the matrix equation, AX equals B, has a solution. If and only if B is a linear combination of columns. Let me recall for what does it mean to be a linear combination of the columns of A? Well, the columns of A are these animals right here. A1, A2, AN, and notice, look what this equation says. It's exactly what this is saying. It's speaking to me. There's voices again. And it's saying to me, this is a linear, B is a linear combination of these columns, right? Number times first column, number second column, number third column. That's what it means to be a linear combination. So if this has a solution, then this vector B is a linear combination of columns. Right, okay. So making these kind of connection observations like this is actually going to be important as we move forward with the theory. The more of these connections we make, okay, system of linear equations, that corresponds to an augmented matrix. What is this augmented matrix? What does it mean for this augmented matrix to have a consistent solution? It means that this B vector here is a linear combination of columns. So let's get practical here. Let's actually do some, I'm gonna do a couple of things here. The first one I think is kind of not too bad, but I want to make sure that we take base on it. So, example. For what vectors does the matrix equation now? can't really answer this question properly until I tell you what A is. So let me tell you what A is. Let's let A be. Can anybody answer the question? Just by looking at it. So here's the equation we have. A is what size is that? 3 by 3. And it's supposed to AX equals B. It's supposed to end up with a 3-row, 1-column matrix. And so my X, what size should X be?
3 by 1.
Good. That's exactly right. So X X necessarily needs to be a 3 by 1 to balance everything out because my B has to be 3 by 1. But, so the question is, so let's write this out. Now, I asked for what vectors B, so let me just make up some stuff for B and see when I. So the question's really asking, for what makeup of B there can I actually solve this equation? This matrix equation. Can anybody answer this?
Doesn't it not have a solution since 0 cannot equal to 3 for the bottom row?
Well, no, actually, this doesn't. Anyway, it does have a solution.
E1, EX1, E2, X2, and then E6, X3.
Okay, I think you're on the right track there. So another way to look at this, so if we're not used to the augmented equations yet, let me do kind of what you was doing. Let me pick this apart. This really corresponds to some equations, doesn't it? In fact, think about multiplying this out. This first equation, this row times this column, thinking about our matrix multiplication, is, well, let's kind of take this up here. When I multiply that first row of matrix times a column vector, this is x1, 0, x2, x3. So this is x1. Agree? The second entry is 0x1 plus x2 plus 2x3. And the last one's a little easier. This row times this column is 3x. Now this animal needs to be the same as this, right? So I've got these equations. And we've seen this before, the way we kind of deconstruct this, right? This corresponds to the system of equations, x1 plus x3, b1, x2 plus 2x, b2, and x3x, that is equal to 3. Everybody agree that's a proper interpretation of what we have going on there? Now, my question is, when can you solve these? Or what values of B can you solve this equation? What's up?
1 and 2.
I can't argue. You are correct, but it's more general. Yeah. Everything It does not matter what B1, B2, and B3 are, you can always solve it. Watch me do it. And there we go. I've got my X3. Am I okay with that? So got that. Now that I know what X3 is, I can put it back into this equation. And I get X2 plus 2 of these. Right? So now I've got X2 is equal to B2 minus 2/3 B3. Correct? And now I know what B2 and B3 are, so I can certainly get B1. Let's see, so I get X1 plus X3, which is 1/3 B3 equals B1, and I get X1 is equal to B1 minus 1/3. No matter what, no matter what B1, B2, and B3 are, it doesn't matter. I can solve it because it's essentially boiled down to this and different problems. You always solve this. So if I look at the equation AX equals B for this particular matrix A, you can always solve it. Am I okay with that? Let me change the game a bit. What about this similar problem, similar example? Same question. And here, I think my matrix a little bit different. What am I going to do here? I'm going to make this matrix 1 minus 1, 2, 2, 3, negative 1, 3, 7, minus 1. Right? 1, 1, 2. Right. By the way, let me ask you all a question. I know, forget what AX is. It doesn't, A doesn't have to be a specific thing. Let's suppose A is 3 matrix. Actually, you don't need this. Let's suppose we have this. I'm not even going to tell you what the matrix is. I'm going to keep it a secret for now. I know one value of the vector B where I can solve this, no matter what. Anybody tell them? Think silly smart aleck. Yes. 0. That is correct. One way that I will always be able to solve this is if B is the 0 vector, right? If this is just a column of 0, right? How can I solve this? I don't care what A is. What solution would I have for X that will make this work? X must be a 0. I can make X a column of zeros. There may be others, right? But at least I've got that. For sure, I've at least got that. Right? So in all these problems here, when I ask this question here, what vectors B and R3, does this have a solution? For sure, B equals 0 vector will work. Question is, there more? For this example, everything worked, including the 0 vector, right? Let's see what happens with this. Well, let's set things up like we did. Let me be that vector here. Okay, so let's kind of take this apart. Let's look at AX, which is 1 minus 1, 2, 2, 3 minus 1, 3, 7 minus 4. Okay, before I run the part now, let me multiply this out. This and actually, okay, let's just try this. Okay, and see what it tells us about me, because I think in the process of me trying to solve this, it's like unraveling a mystery. While I do this, it's going to tell me some crap that needs to go on to make me work out. So, as opposed to what we did last time with the equations writing out, I'm going to do sort of the more sophisticated form, but we can use from the last one and it's better in general. I'm going to write the augmented matrix. No, I'll start with it anyway. So the augmented matrix should be 1 minus 1, 2. We sort of suppress this vector right here, just like earlier when we did augmented matrices, we suppressed the variables. 2, 3 minus 1, be 2, and 3, 7 minus 4, be. Okay, what I am going to strive to do is I am going to try to bring this to row reduce echelon, right? That's my big goal here. And I'm going to go about this systematically. The first thing I'm going to do is I'm going to use this 1 up here to take out that 2, to take out that 4. So I'm systematically going to turn this into a column 1, 0. So my top row is going to be the same. So I multiply by -2 and add to the second row. Multiply by -2 and add, that's a 5. Multiply by -2 and add, that's a -5. Multiply by -2 and add, and I get B2 minus 2B1. Everybody okay with that? Now I'm going to use this to take out that 3. So I'm going to multiply this row by -3 and add to the bottom. And I get 0 times -3 and add, so this would be 3 and 7 is 10. Times -3 and add, so that's going to be -10. And times -3 and add, that's going to be B3 minus 3. Right, okay. Yes.
Shouldn't it be B1?
What's that?
Shouldn't it be B1?
It sure should. Yes, thank you very much. Previous one, thanks. Now, there's something kind of obvious to do right here. And so let me just take, I'm going to do this correctly. 1 minus 1, 2, B1, 0, 5 minus 5, B2 minus 2, B1. I'm going to multiply this by -2, add 0, 0, 0. How about them numbers? All right, everything's gone on this side of the dotted line. We'll see, what did I do? I multiply by -2 and add it. So it's negative 2 and add, so it's going to be 4 B1 minus 3 B1 B1. This is going to be minus 2 times this plus this. That's going to be B1 minus 2 B2 plus B3. And actually, I'm going to forego going on the web road with this echelon form, so I don't need it, because I can answer my question. Here was the question. So what vectors B and R3 have a solution? Well, by the way, how many, so this is good review here. How many pivot columns do I have? Good, I've got 2 corresponding to this, and I need to clean this up a little bit, but this will be a pivot column. Everybody okay with that? And then, now, look at that bottom row. What do you need to have happen for this to have a solution? Remember, that's what the question was. We have to have a solution. Yes,
The thing on the far right. Sure.
that is correct, right? This equation is 0 equals Fred. Well, Fred better be 0, otherwise you're done, right? So for a solution to exist, B1 minus 2, B2, B3. See? And that's the only equation. There's just that single equation. If I were to solve the single equation, notice I've got one equation, 3 variables. How many free variables do I have? Well, look at the augmented matrix. What's the row reduced echelon form? Already there, right? There's only one freaking row, right? How many pivot columns do I have? 1. It's just the right, I mean, column seems like a silly word, right? It's just a number, but I just got 1 pivot column. How many variables did I have? 3, right? So there are 2 free variables. So B1 is the basic variable. So what does a vector look like for which this is solvable? It looks like this. B2 is free, B3 is free, and B1 so if you can write your vector B in this form, bottom 2 can be anything, but the caveat is the top one has to be twice the middle minus the bottom, then you can solve this. Notice that the 0 vector is one of these, right? Because if you let B2 and B3 be 0, and so is that. Okay, I'm going to report one more theorem for you, and that'll be that. And you probably have noticed a lot of this next theorem in what we've been doing. Theorem. Let A be R in by N. The following are equivalent. By the way, when I say that, that means if one of these is true, then all of these is true, and if one of these is false, then they're all false. For all B vectors in Rm, so that's an M row vector, Ax equals B as a solution. If that's true, then each B in Rm is a linear combination of the columns of A. Three, another equivalent condition is the columns of A span, that is to say, every possible n-dimensional vector is linear combination of columns. And finally, A has a pivot or a pivot position in each row. Look back at that example, and you'll see that in the example we had a pivot in the row. There's one more theorem that I didn't cover, and that is theorem 5 in your text in 1.4. Just look at that, record that theorem in your textbook, and we're going to talk about matrix multiplication more generally later. That will be something about the law. Any questions? All right, you all have a good one, and we will see you all.